welcoming Dr. Tarun with us from ICER. And I was just sharing a couple of minutes before that this pandemic has also given us a unique opportunity to listen to extremely good lectures. And those of us who are not from the physics stream, again, revise it on the YouTube. So whatever we have not been able to understand, it gives us an opportunity to listen over and over again, and a great learning experience. So on behalf of Hindi Vidya Prachar Samiti's Ram Niranjan Jhunjhunwala College, I extend a very warm welcome to Dr. Tarun for accepting our invitation, and I'm very sure your lecture is going to be equally exciting. And to all the participants who have joined both on the Zoom session as well as on YouTube. And I'm also thankful to IAPT for the trust they have in our college, and to allow us to host these lectures, and to the head of the department, Dr. Rekha Gurpade. Thank you very much, madam, for a very exciting series of lectures that you have lined up. Thank you.
Thank you very much. It's your encouragement, actually. We are doing it. Now, may I call upon Dr. Devidas Gulavde to speak on behalf of IPT regarding few words about the IPT. Yeah, Dr. Gulavde.
Thank you, ma'am. I welcome today's esteemed speaker, Professor Tarun Souradeep, and all participants on the behalf of Mumbai Sub-Regional Council, IAPT. Indian Association of Physics Teacher was established sometime in 1984 by the great visionary late Dr. D.P. Khandelwal, with the active support from few physics teachers, with the aim of upgrading the quality of physics teaching and teachers through a mass movement of dedicated teachers. Since then, this organization has grown to the members of around 11,000 nationwide. IAPT organizes many activities to fulfill its objectives, such as conventions, competition for the students of different level of education, as well as for physics teachers. Furthermore, it publishes monthly physics journal, which comprises of research articles on developments in physics and physics education, along with the highlights of IAPT activities. To realize its objectives, the whole country has been divided into about 20 regions, and Mumbai Sub-Regional Council is one of it. Mumbai SRC is formed in 1998 and actively organizing annual workshops for undergraduate students, which consist of development of concepts using problem-solving approach, and also enrichment lectures related to new frontiers in physics. Mumbai RC also organizes the workshop and seminar for students as well as physics teachers. Further, the current online lecture series is the activity that is initiated during this lockdown. Thank you, ma'am. Over to you, Professor Gurpade.
Yeah, thank you so much, Dr. Devidas Gulavde. Now I request our chief speaker today, Dr. Tarun Souradeep, to please take over the stage, and looking forward.
Introduction, madam.
Yeah, please,
Introduction.
sir, you are. Oh, sorry. Dr. Kiran Kolvankar, kindly introduce our chief guest.
Yes, thank you very much. It is really my great pleasure to introduce Professor Tarun Souradeep. Yeah, he finished his BTech in Mechanical Engineering in Kanpur, from Kanpur IIT in 1988. Then he decided to change over to physics and came to IUCAA for PhD, which he finished in 1995. Then he went on to Canada. He went to Canadian Institute of Theoretical Astrophysics for a postdoctoral position. He was there from 95 to 98. And then he went to Kansas State University, High Energy Physics Group over there. He was there from 1998 to 2000. Then he returned back to India. He joined IUCAA in 2000. And he has past 20 years, he has done enormous amount of work. I mean, I will just briefly tell some important things what he has done. Now, recently, a couple of years back, he has shifted to ICER and he's a chair over there. So all of us know him for his contribution to detection of gravitational waves, which took place 4 years back. He was member of that team which detected gravitational waves for the first time. But actually, there was a lot of hard work behind that. Previous 4 5 years, he was leading a group. He was a lead proposer in a formulation of a group called LIGO-India, which had planned and built up national initiative, which finally led to India's contribution to this gravitational wave detection. And for this work, he got international awards, Breakthrough Prize in Fundamental Physics in 2016, and Gruber Cosmology Prize in 2016. But he was already well renowned world over scientist for his work in cosmic microwave background work. He has done a lot of work in this field, which is appreciated, and for which also he received international award, Gruber Cosmology Prize 2018. His international stature is reflected in the fact that he is elected to the fellowship of International Society on General Relativity and Gravitation. He has won several awards. I will not mention on Indian level also. I will not mention all, but he has received BM Birla Science Prize in Physics and also DST Swarna Jayanti Fellowship Award. He has more than 200 publications, and total number of citations he has received has crossed 16,000. He has many renowned papers. There are 3 papers which have received more than 1,000 citations, and he has 8 papers which have received more than 500 citations, and his H index is 51. This is just a tip of iceberg. He has a lot of contributions. I will not go into that. We are eager to listen to him. Only one request to the participants: you can type your questions in the chat box, and we will try to answer them towards the end of the talk. Thank you. Professor Tarun, it's over to you now. Thank you.
Okay, thank you, Kiran. Can you hear me?
Yes, sir.
Okay, great. So let me begin by thanking Professor Gorpade for the invitation and Kiran for seeking me out after many years. We were good friends many years back when he was a student at University of Pune. And thank you to Usha Mukundan and Dr. Devidas for their kind words. I wanted to give a talk. I want to always take on any opportunity to give a talk on LIGO-India. That's because anytime I connect to the youth, this is a project that is happening for the next generation of people here. And I always maintain that it's our duty to let them know that what is coming up and what the opportunities are and how exciting it all would be. So let me begin my talk. I'll share the screen, and as you've been told how you can ask me questions, so you should please feel free to do so. Yeah, so I titled my talk as LIGO-India Beyond Discovery of Gravitational Waves. And that is to sort of highlight the fact that, yes, we were part of the gravitational wave discovery, part largely due to the fact that, we were already planning for the LIGO-India project from 2011. And so this sort of talk will try to highlight what the challenges are in this field, and why this is an exciting area and what lies ahead. I mean, the discovery, yes, this is a great discovery, but it was not just a one-off event. This was the kind of discovery which opened a new window into the universe. So I won't be amiss if I compare this to Galileo's telescope, which opened our eyes to the universe in the electromagnetic waves. this has opened our eyes to the universe in an entirely new, you know, uh, to an entirely new messenger from the universe, which is these gravitational waves. So let me start by, telling you what the uh, discovery was all about. So all of you would know from your, even from your general interest in physics, that we have a, theory of gravitation given by Einstein, which sort of overrun the theory of Newton's, which held sway for many decades, and of course explained for us the orbits of planets. But this new picture of the what we call the force of gravitation was very, very, what would I say, very revolutionary. It was the first time that we realized that space-time as we know it is not just a passive stage. It's actually a very dynamic fabric which takes part in the dynamics of matter. So, there are these two lines which are made very famous by John Wheeler, which said, encapsulates what GR is all about. It says, matter tells space-time how to curve, and space-time tells matter how to move. So this is the story of gravitation. So the Earth moves around the sun because sun has created a curved space-time around it, where the Earth is actually moving in a straight line, which happens to be the ellipse that we observe. And similarly, if so the matter has told space-time how it is, and so it matter of the sun has curved the space-time, and Earth is following what the space-time tells it is the straight path. Okay. So now it always was an immediate consequence that if space-time is like a fabric, we typically know that if there's a stretched membrane and if we, sort of perturb it, there will be waves generated. So similarly, what happens is that matter in motion creates space-time ripples. These are called gravitational waves, and these were predicted within a year of the formulation of general theory of relativity, and in 1916. And these waves are very, very similar to the waves that we are more familiar with, which is light, and which is um, we know that the speed of light is a fundamental constant, and the gravitational waves actually travel at the speed of light, which means they are massless excitations. And they're just like light is transverse and has two states of polarization, so do gravitational waves. But this part, the fact that gravitational waves exist, was a very, very prized prediction of GR, because it was the most major deviation from Newton's gravity. It was qualitatively a unique prediction beyond Newton's gravity, because many of the effects that you see in GR, which are corrections to Newton's laws, can be viewed as such. You can think of a corrected law of gravitation to try and explain some of the effects of GR, although it's not easy to do so, but you could think of that. But it is very well understood that Newton's gravity did not have any place for traveling waves like gravitational waves. And that's why the fact that we are now routinely measuring gravitational waves is a major, major breakthrough that happened in 2016. So people who follow science news would have seen a lot of articles come out today about event that was announced yesterday by the LIGO-Virgo collaboration, and we are part of that. And there were news articles in all your papers about very, very enigmatic event where we think there's a new class of objects which lie in mass range between the masses of neutron stars and black holes may have been involved. So this is how it is. I mean, this is a rendering of how you should sorry, I don't think I can get the videos. I can. This is how you should visualize what's happening with gravitational waves. So imagine two neutron stars going around each other. And why am I talking only of neutron stars and black holes? That's because neutron stars and black holes are extremely dense. And gravitational waves are very weak, and gravitational waves strong enough to be detected can be only generated by astrophysical sources which have masses of few to tens of solar masses, which are moving at very high speeds. So then this motion has to be violent and with very heavy masses before a signal that is detectable is generated. So what was the signal that was generated? Before that, I should also just mention that this prediction was made by Einstein in 1916. So 2016 was exactly a century from the prediction. So these are cutouts from the original paper of Einstein, and you would realize that as in many things in science, when Einstein predicted gravitational waves, he actually said in any case, well, it cannot be thought that the amplitude would have he just thought it would have vanishing values and of not very practical use. So this is to answer a lot of times when people question us about would there be uses of gravitational waves. Just like when we knew how to create electromagnetic waves and detect them, in the Hertz experiment, and uh, you could ask, you did not know that one day we'll be carrying devices like your mobile phone, which is kind of generating and receiving electromagnetic waves in the radio frequencies, and allowing you to do day-to-day work. So we don't know what would happen in a century. Just like Einstein didn't know that in a century from his prediction, a team of dedicated scientists would actually detect gravitational waves. So this is how it happened. So long time ago in a galaxy far, far away. So this is taken from a Star Wars kind of starting shot. So it actually is in a galaxy which was 1 billion light years away. And if you were to look up at the sky of the galaxy, you'd see something like the Milky Way. But, there would be a region, if you zoom in, with high resolution, which would be devoid of any light. And these would be these two black holes sitting next to each other. And they have very strong gravitational fields. So you can see that the field of stars that you're seeing beyond them is kind of distorted very visibly. So that is kind of a very nice measure of the gravitational field that black holes exert. And as I'll start the movie, you would notice that these black holes cannot be sitting quietly next to each other. These are massive objects, so gravity will pull them towards each other, and they actually rotate around each other, orbit around each other, and finally merge. And this is what you'll see. And the background of stars will give you a feel for the dynamic evolution of the space-time around these black holes. So light is coming through the space-time between the black holes, and you'll see that markedly change. So you can see that these remarkable amount of activity is happening in the stars behind as these black holes churn up space-time and create gravitational waves. So it always reminds me of taking two sticks and churning up a muddy bucket of water, and you'll create waves. And just like that, there are waves created here. The black holes merge and form a single black hole, and you can see that there are these final oscillations of the stars as the waves pass through. And these messengers traveled over 1 billion years and brought this news to Earth on 14 September 2015. LIGO detectors, one at Hanford, Washington, another one at Livingston, Louisiana, about 3,000 miles away. And then this at one go was a hat trick of detection. So this was, of course, the first direct detection of gravitational waves by human apparatus, which is the most notable achievement. And then this was also the first detection of black hole. So the black hole, as I showed you, when after merging quivers, and this quiver was first, in fact, this is called black hole ring down, was first predicted by Professor Vishweshwara, who spent most of his career in Raman Research Institute and later in Indian Institute of Astrophysics in India. But as a graduate student in Maryland, he had predicted this ring down signal of black holes. And then this was also the first detection of black hole binary system. So we knew that black holes exist, and they also exist in pairs, such that there can be interesting dynamics of black hole binaries. So all this makes for an amazing treat that we had in 2016 in the scientific world. And India was already a part of this, even before we thought of LIGO-India. I talked to you about the black hole ring down signal, but in Ayuka many years ago, when, as Kiran recalled, he was a student in master's in Pune University, and I was a graduate student in Ayuka. Professor Dhurandhar there with his then postdoc, Professor Satyaprakash, who is now one of the leading scientists and works at Penn State University, did some foundational work on the data analysis required to pull these weak signals out of noise. And simultaneously also there was another effort led by Professor Bala Iyer at Raman Research Institute from the 90s, which worked out the foundations of source modeling. It told you what kind of signal to expect from coalescing black holes. And so India had been a part of this whole game from then. And in fact, in the early 90s, as a graduate student in Ayuka, I had seen an attempt to build, make a proposal to build a 100-meter gravitational wave, prototype detector, which at that point did not go through. But in 2011, when we put this proposal for the LIGO-India detector, that has, of course, that's on its way, and we are, making good progress, as I'll show you later. So to explain what is happening, this churning of space-time a little more, I have this video, I think, which sort of connects the signal that you see at different times during the merger of two black holes. So here in this picture, you have this black hole, and there's another black hole which will show up. It's outside the frame now. But what I wanted to point out is the colored panel, there below, which marks out, the color marks out the depth of the potential well. So you can imagine the black hole is a very dense object, creates a very deep gravitational potential well. And that is represented in this red color, and then going to orange, yellow, and then green. And as you go to bluer colors, the gravitational potential is going to zero. And there's similarly another gravitational potential well around the other black hole. And as these black holes will go around each other, you will see that the space-time between them kind of dynamically evolving. And the dynamics is seen in these arrows that show you the flow of momentum in space. Okay, and that is very important to realize, that this aspect was missing totally in Newton's gravity. In Newton's gravity, all you have is a gravitational potential. You don't have these momentum fluxes, which GR allows for. So let me just start this movie, and let's watch how gravitational waves emanate from these pair of black holes. And we zoom in now, to see the structure of space-time fabric near the black holes. And initially they are orbiting almost, in a regular orbit like our sun. And so you can see the trace, blue trace going over this sinusoid below. And this is basically the signal that would be emanating and coming to the detectors. As the black holes get closer and closer, the frequency increases, and so does the amplitude. And the amplitude really grows really high as the black holes almost touch each other and create a common envelope. And you can see two deep holes, and they're sort of getting connected. And then the movie is frozen to show you that, there's almost like spilling out of space-time there, which creates this gravitational ripples which you see in magenta going out of the movie, in the movie going out. And these travel for years before they get to another detector and get detected. So what these reveal for you, any of the gravitational wave events reveal for you physics happening at the extremes of energy. And to emphasize that, let me tell you what happened in this first event. So there was a 30 solar mass black hole and a 40 solar mass black hole. These black holes pack the amount of 30 suns worth of matter into a diameter which is pretty much the diameter which would compare to your size of Mumbai, right? The diameter would, if the black hole was to be put here, Mumbai would be a typical scale, and slightly bigger, maybe the greater Mumbai, everything together will be the 40 solar mass black hole. These two moved in orbit around each other. And as they moved in orbit, here's the trace of the velocity versus time. And you can see the green curve, which is the relative velocity of the black holes. As the separation, which is the black line, decreases, okay, you can see that the velocity reaches almost beyond actually crosses more than half the speed of light. Okay, so now these kind of velocities, of course, you would have heard of in talks of Large Hadron Collider, where particles moving at almost the speed of light crash into each other. But here, imagine 40 solar mass worth of object, dense object, which is the size of a city, crashing into another one at a speed of light. So this is a kind of amazing laboratory, and that generates, of course, huge amount of energy. So in this first event and many other events, similar numbers came out. 3 solar masses worth of energy was converted into gravitational waves. So you know that mass and energy is convertible. So that is how fusion and fission reactions work, right? So there's a mass difference. But this is kind of at a very different level. Here, you imagine 3 suns worth of matter suddenly getting converted to energy. Okay. And the sun is a bright object which shines so brightly for us, only converts very little of its mass every second to create the energy that it is creating. Right here, what happened was, for that 0.2 seconds, the amount of energy that was coming out of the system was equivalent to the electromagnetic emission of all the stars in the universe. Okay, so this is the kind of scales. These are the most energetic phenomena, and these are more energetic than anything that we have seen in the electromagnetic spectrum, and hence in the universe. Similarly, there have been another exciting result. In the previous case, there were 2 black holes which merged into each other. Black holes typically, after some time, eat up all the matter around them, so don't emit any more light. So they are not visible. The black hole binary merger is not expected to give out any fireworks or light. However, if you, instead of black holes, think of neutron stars. These are again very dense, not as dense as black holes, but fairly dense. So a neutron star has the mass of the sun packed into a radius of 10 kilometers. And it is so dense that matter exists as neutrons. The nuclear matter behaves like the entire star behaves like one nucleus is as dense as the nucleus of an atom. Okay. And two neutron stars colliding into each other created not only gravitational waves that were detected by LIGO, but also created electromagnetic waves that were detected uh, first by gamma ray observatories, Fermi and Swift, and then later in X-ray, optical. In fact, this event was so important that 70 observatories, which are marked in blue around the world, followed up the observations here. Okay, and 70 observatories included 7 space observatories, which followed up this event. And this revealed for us a whole wealth of information. So, for example, many of you, and I come from the field of cosmology, one of the measurements that we have done very well with Cosmomicro background is the measurement of the Hubble's constant. This provided an independent measurement of the expansion rate of the universe, which is called the Hubble's constant. Although this is nowhere as sharp as the measurement by Planck, which we were part of, the one in cyan line here. But this is the beginning. So you can see that gravitational wave observations will start making important statements about cosmology. Also about something that all of you must be very curious to know. Where did all the gold? We treasure gold. All our world's economy used to be counted in amount of gold that was held by various countries. Where did all the gold come from? And gold, in fact, although many heavy elements are cooked in stars and then thrown out when the stars die at supernova, the amount of gold created that way was known to be inadequate to explain the abundance of gold on Earth. Right? So the only other solution was to create gold when such neutron stars collide into each other. And when these heavy elements like gold are created, they are very characteristic signatures seen in the electromagnetic spectrum. And those were seen in this event, which confirmed this, our cosmic understanding of where these heavy metals like gold, platinum were created. So till now, the LIGO and the Virgo detector in Europe, the two LIGO detectors, have detected, have published 11 events from the first 2 runs. And, there were 50 candidates in the third observing run, Prof, which some of them are being now announced one by one. So a few days back, there was one very interesting black hole merger event that was a few months back, maybe a month and a half back. And then yesterday there was this neutron star and possibly a neutron star black hole kind of in something in between those two merger that came up. So this is an exciting field with news that's coming out almost at a few weeks level, and this is kind of going to be this situation. And in India, we are involved in many of this. So I just wanted to emphasize that, LIGO India is one part of the story, and we also have a LIGO India scientific collaboration, LIC, which actually carries out many of these searches and works on various other signals, the test of general relativity, and such exciting areas of science with gravitational wave observations. Now let me tell you about LIGO India and get to why the gravitational wave observatories are so unique. And that has to do with the signal that you are trying to measure, the strength of the signal that you're trying to measure. So if you looked at the first event, the peak strain, so gravitational waves are actually strain, they stretch space-time. So the lengths change by a delta L. Just like if I take a bar of metal and stretch it, I know that the strain is given by delta L over L. The strain of a gravitational wave, of the gravitational wave that was detected in the first event, was 10 to a minus 21. Okay, so that's a very tiny number. So even for a detector which was 4 kilometers long, this meant that the displacement that we measured between the mirrors, and I'll explain to you where these mirrors come from, was at the level of 10 to a minus 18 meters, what I call attometers. Okay, this is at the cutting edge of what measurement possibilities that we have. So these are the most accurate large scale physics apparatus that you have. And just to put in perspective, 10 to a minus 18 is orders of magnitude smaller than the size of the hydrogen atom, in also a couple of orders of magnitude smaller than the size of a nucleus, right? And we measured displacements of that level using these detectors. So in some sense, if I want to say what was required to uh, measure gravitational waves, it was just like breaching a frontier. So we know that in daily experience, we experience sizes from about megameter, which is when you travel from one country to another, to about millimeters is something that we regularly talk about in day-to-day life. But we know that we talk about things at atomic level. We, physics, we talk about nuclear physics, which is at the level of 10 to the minus 15 meters. But this ability to measure sizes of 10 to a minus 18 meters, this breaching this frontier of ability to measure, is what was required to measure gravitational waves. And hence there was this immediate, the next year's Nobel Prize was given to these three gentlemen. So Ray Weiss devised the experimental setup which would measure gravitational waves, which is this LIGO detector, laser interferometer gravitational wave observatory. Kip Thorne was the person who kind of laid out the whole science of what gravitational waves, what kind of information they carry, and what was the importance, and how to predict them. Many important things. And the third person is not as well, maybe not as well known to students here. He is actually a very well known particle physicist, experimental particle physicist in his own right, who came to the field of gravitational waves to lead this whole team of scientists and engineers to build the LIGO detector. And this is something that is often not talked about as much. The ability to create a team of 1,000 scientists and detector engineers and build a detector that can work towards a scientific quest over many decades. For decades they had no signals, right? So these LIGO detectors were first switched on in 2001, and for 15 years they had no signal. So they did not detect any cosmological signal. So it requires a huge effort and huge capability to be able to keep such a science team going. Nevertheless, when this discovery was there, I should point out that there were 37 authors from 9 Indian institutions in that discovery. And this itself was, pointed to the importance of Indian scientists getting involved in major, what I call mega sciences. So that is a very exciting possibility that can involve many students and researchers with various different diverse capabilities. It's not just you have to be extremely good only at solving equations, or so there are people who are good at sitting and working for painstakingly for hours to debug one of the interferometer problems, or someone who can build some wizardry in electronics, or some feedback systems. The scope of contribution is becomes immense in these major collaborations. And so this LIGO, in my understanding, is the discovery was the first time there was such large numbers of Indian scientists already engaged in this science, both experimentally and you know in data analysis. So this is what happens. This is the physics of the detection. So as the gravitational waves moves through matter, so in the left you see lattice of particles in a square lattice, and as the gravitational wave goes through, the distance between these particles change, right? So it distorts the amount of space between particles. So it's stretching and of space as the wave passes through. Now, if I were to monitor a ring of particles amongst this here in the right, you see as a plane gravitational wave passes through the plane of the screen, the particles are expected to do this dance. They will change from the circular configuration to an elliptical configuration, and then back to a circle, then back to an ellipse in the 90 degrees apart. And this is what goes on. Now, how do I measure it? So, of course, if this happened as visibly as it is happening on the screen here, that wouldn't have been a problem. But the point is, these red dots are moving, in fact, at 10 to the minus 19 meters. And, you need to be sensitive at the level of 10 to the minus 20 meters to be able to pick these up. So, the best bet we have is to use laser interferometry. And many of you students may be aware of this very commonly known setup called the Michelson interferometer. So at some level, the gravitational wave observatories that we have are large-scale Michelson interferometers. You have in your labs, small-sized tabletop interferometers. Here, this thing is built over kilometer scales. But the idea is the same. Laser light comes and is split down two paths to two mirrors and then come back. And if the distances are exactly the same, then there is no light seen in the output detector. But if a gravitational wave was to pass through this detector, then you would notice that one arm would stretch and the other arm would squeeze. And then you would see some light in your detector. And this is the principle which underlies gravitational waves observations. So here are two pictures of the gravitational wave observatories that are running in the US and Hanford, Washington, and Livingston, Louisiana. These are 4-kilometer, arm length Michelson interferometers. To be more correct, these have Fabry-Perot enhancement, so in cavities, but I think that's not important to get into. But this is how amazing the whole setup is. You can see that there's a person actually standing inside one of the beam tubes to install what I call baffles. There's a laser light passes through this beam tube, and this beam tube is actually evacuated to ultra high vacuum. And so on a large scale, this is the largest scale vacuum system you have. You can see the size of a person here in this first top left picture compared to the chambers, vacuum chambers that are involved in this experiment. And on the top right, you see this 4-kilometer long length of tube, which is covered by a concrete shell. So it's a amazing setup inside. The optics is, the mirrors are, sizes which you do not be able to carry on your, one person cannot carry them. These are 40-kilo mirrors, and they hang from very interesting mechanical suspensions. And these mirrors are amazing surface finish. they're 100 times better surface finish than the best telescope optics that we have. And this itself, by itself, attaining such capabilities are actually path-breaking technology. And in fact, RRCAT, Center for Advanced Technology at Indore, has been already working for the last few years in achieving such capabilities. And then the suspensions from which they hang have to be very, very intricate. So they have to have a mechanical cue, which is how pure is the note of 10 to the power 8. Okay, so if this system is supposed to be put into oscillation, the oscillations are almost pure note. Okay, and this entire apparatus is shielded from the movements of the ground. The ground at any point on earth shakes at about a micron all the time, even when there are no earthquakes. If you go anywhere in the world and go to measure the motion of the earth, the earth keeps at low wavelengths of hertz region. It's always moving at a micron, and you have to then isolate that by 12 orders of magnitude to see the signal that you want to see between the mirrors. Then the lasers themselves are very unique, not because of their wattage. These are 180 watt lasers. So of course these are uh, certainly very high power. You wouldn't definitely not want to put your hand in the path of any of these lasers. But on the other hand, these are not those ones which cut through steel kind of lasers. Those are pulse. These are continuous lasers. And so continuous lasers of target power of 180 watts. But the important thing about them is their stability. Their line width is, these are pure monochromatic waves up to the level of 1 part in a billion. So these are sub kilohertz line width in an infrared laser. Okay. Similarly, the intensity of the laser doesn't fluctuate by more than 1 part in a billion, and the stability of the frequency is also, parts per billion. And this is a unique, kind of apparatus. The laser itself was developed in Germany by a German team of researchers. But there are similar lasers which were developed in Australia, but this was the one which was. But the main idea is these narrow line width lasers have many, many applications far beyond gravitational waves. Of course, if you have something whose frequency is very standard, then you can use it as a clock. And then you can also, given the stability of the laser, encode quantum keys, and quantum encryption can be done using such lasers. So these lasers are involved in such things. And then what is very exciting is LIGO is improving day by day, and now getting to a regime where we are actually worried about the quantum mechanics of the mirrors themselves. The mirrors are 40 kilogram objects, and as you know, nothing in this world is classical. We are governed by quantum physics. So, the fact that I don't look like a fuzzy object is because I'm a very massive object. So on the average, the fuzziness doesn't show up. But for a 40 kilogram mirror, the quantum fuzziness actually is competitive with the displacement of the mirror that you're trying to measure. And human ingenuity has been such that we have been able to harness this to actually improve the detector sensitivity even further by a factor of 10. So that is what we are doing in, going from the current generation of detectors to the one that will be set up in LIGO-India would invoke quantum measurement with something called squeezed light. And that again is actually at the forefront of quantum technologies and quantum information. And this is an extremely exciting area for Indian students to get involved in. In fact, at IISER Pune, one of the speakers mentioned that I moved to IISER Pune about 9 months back. And one of the reasons for moving from IUCAA to IISER Pune, I'm still on deputation from IUCAA, but I moved here basically to, kind of spread out the work of gravitational wave related science that overlaps with such sciences of quantum technology. And that effort is ongoing in IISER Pune. So in fact, we have put forward a proposal for a quantum technology hub at IISER Pune to DST. So where does LIGO India fit into the whole picture? So LIGO India fits into this picture if you are looking at the sky, shown in this dark circle here, and wondered, yes, LIGO did detect two black holes merge, but could it tell you which part of the sky the signal came from? And there, LIGO could tell you that only up to the accuracy of this big patch that I'm showing with the cursor. I don't know whether you can see the cursor, but this is the large patch of the sky which would fit 7 Saptarishis, the Big Dipper. 7 of them would fit into that sky. So with a huge uncertainty in position. But if LIGO India was in operation at that time, then this would have shrunk by a factor of 100 to this bright, ellipse that you see here. That would have been the accuracy. And then we would be able to do astronomy with gravitational wave observations. So the LIGO India project observatory, when it comes up, will make a huge difference to the kind of science that we are able to do with gravitational wave observatory. So this LIGO India project is shown here. It's a actual 3D rendering of the civil infrastructure drawings. There's in fact a very nice movie made on this infrastructure that is coming up. And you can see the 2 arms of the detector stretching out, and the central station where the laser and all the other many vacuum elements would sit, and various other parts of this beautiful campus, which will be located in Maharashtra, in the Hingoli district of Maharashtra, near a town called Aundha. It's a very small town, in fact, hamlet of Aundha. So we have now in a state where a site is acquired and we have formally into the construction phase. And there are 4 lead institutes involved in it: the Rajaramana Center for Advanced Technology, the Institute for Plasma Research in Gandhinagar, the IUCAA and in Pune, and the Director of Construction of the DAE. And so this is funded by DST and DAE together. It's one of the mega science projects. And as I said, the Indian proposed commitment is the construction operation of the entire detector, all the infrastructure, including the 8-kilometer long ultra-high vacuum system with its controls. And then inside that, we'll set up the detector. Many parts of it will be built here. But the key hardware components like the mirrors and the laser, which I told you were unique globally, are being provided by the LIGO Labs US under this Indo-US collaboration. And we'll have very close technology collaboration on this project. So just to summarize, LIGO India would allow full exploitation of gravitational wave observations. At this point, we are able to see gravitational wave observations, but these are, kind of the amount of astronomy we are able to do is not much. But with LIGO India, we will be able to do a lot more of astronomy. Setting up something like LIGO India would involve high-end frontier technology, so it would be transformational for Indian labs and industries. As I said, India provides a geographical advantage of a huge baseline, which kind of allows you to triangulate the position of the sources in the sky. But it also has something that is not often as much talked about. We also have a demographic advantage. India is one of the few youth-dominated populations in the world. And this is very important where you have a major undertaking like LIGO-India coming up. We believe we can grow the group of teams much faster in India. We have excellent undergraduate system, and this provides excellent opportunity for undergraduates and postgraduate students to get into exciting areas of science and technology. So this project was, flagged off with a big bang in 2016 in February, and there was the MOU signed in March 2016, about a month after that, between US NSF and DAE and DST, Department of Science and Technology, and Department of Atomic Energy. And you can see that the PM made sure that he was personally present at that, and then he met team members later, and there's been a very strong recognition and push at a top level to see this project through. And the reason for that, again, to emphasize, is this just not a simple physics experiment or astronomy observatory. This encapsulates many areas of science and technology. So in green are the areas of astronomy, in yellow are the kind of physics questions that it will address, and then in red are the kind of engineering technology which it will push to its boundaries of worldwide expertise. And then this is a precision measurement, as I said. And there's of course people interested in computing, grid computing, and data science and machine learning. All that is there in huge amount in this field. So what do we have to do to get LIGO-India going? So we'll of course have to build 8 kilometers of civil infrastructure to create the base. And on that would sit this vacuum infrastructure, which will be the largest vacuum infrastructure in the world, just like the other two LIGO labs. So it will have 10 million liters of space, which is evacuated to, nano torr vacuum. Okay, so millimeters of mercury. And then inside this vacuum chamber will sit a very intricate layout of optical elements. This drawing is a much simplified version of what will actually sit in the real LIGO detector. But this sort of tells you how difficult the apparatus is to work with, and what challenges we may be facing in getting this going. But we have made great progress. So since 2011, I was personally leading the search for the site because, of course, you may have all the science and technology, but you need to have a place to put the LIGO-India site it. And LIGO-India also comes with very strict requirements of seismic stability. So we had to look in low seismic zone areas. So we looked at about 40 sites and did seismic studies, and many of them, and then finally homed in 2016 after 5 years on the final site. And this is how the site looks, and I've of course personally very attached to it. So here's a picture I took in pre-monsoon time and in this bloom of spring where palash flowers bloom there. It's very beautiful then. And post-monsoon, it all turns green, as many places in this area do. So this is in the Marathwada regions, which is fairly dry, but it has its own beauty, kind of a rugged beauty. And a lot of activities are already on the site. If you go there, you would see various pillars marking out the perimeters of the site, the location of the center station, and along the lines of where the beam tube will lie. And then there were geotechnical studies done where we bored 30 meters into the ground to study the strata of the rock. We also excavated parts of the land to see the speed of excavation, sorry. And then as in India, you need to fence up your territory. So there's now a fence stretching across this, huge perimeter of the LIGO-India project. And also in RRCAT, we are setting up something called the LIGO-India Offsite Facility, which, as you see in this picture, is fairly, advanced in construction, where we will have a 10-meter prototype on which most of the training of the people would happen before they go on to start installing the detector on the site. at the site. Okay, so this is a picture of 6 months back. So maybe this is much more advanced by now. The work is going at full speed. I mean, of course, there was this COVID interruption. I don't think it has, work has been going on for a couple of months now, but it is going well. So finally, let me end by pointing out that this exciting area of LIGO India and LIGO physics is only one of the windows of gravitational wave astronomy that will open up in the next decade or so. Okay, and this is looking at gravitational waves of millisecond time period. Okay, so just like light, we do astronomy with radio waves, ultraviolet, then visible, ultraviolet, infrared, at different frequencies bands. Gravitational waves will be also studied at different frequency bands. So at milliseconds is the window that has opened with LIGO detectors. In 2030s, there will be a space detector called LISA, Laser Interferometer Space Antenna, which is already a approved project of the European Space Agency, and is very, very eagerly looked forward to. This will see another different class of objects, and also see some objects much earlier than in LIGO. So you would see them first in LISA and then predict when it will be seen in LIGO. And these have wave periods of about minutes to hours. And then you can use radio observatories, like the GMRT is in part of this pulsar timing arrays. So the global pulsar timing arrays, which monitor pulsars and use them, the fact that pulsar is excellent clock, use them to measure gravitational waves on very, very long wavelengths of parsec scales. And these are years to decades in time period. On the cosmic scale, there is an amazingly prized signal that is awaiting, and some of you may have heard of it. This is the gravitational waves generated at the beginning of the universe, at Big Bang, right? And this is to be measured. This will be measured in the cosmic microwave background, polarization of the cosmic microwave background. And that's another area, and some other day that I will talk to you about a proposal that we have put to ISRO for taking part in this arena of gravitational wave astronomy. Okay, so I'll stop there and take questions. Thank you.
Yeah, thank you, sir. We will take questions which are there on the chat box now first, and then we will
Okay.
see what can be. Okay, yeah. Shall I post a question, sir?
Yeah, let me see.
I'll read from the chat box. Yeah, you
Okay.
can. So that the first question is asked by Raja Nadarajan. Sir, please clarify me that the time dilation and length contraction of special theory of relativity still holds for general theory of relativity. If not,
Yes.
how it differentiate from one another?
No, time contraction and time dilation and length contraction, everything of special relativity holds in general relativity. General relativity does not change the physics locally. General relativity tells you that special relativity is the theory of physics at a point. Gravitation manifests itself when you want to look at the physics in a region bigger than just a point. So, for example, let me tell you, I mean, this is how GR works. I mean, locally, if I put you in a closed box, which is often called the Einstein's elevator experiment, you should not be able to detect gravitational field at all. It is indistinguishable from acceleration locally. The reason we know that Earth has gravitational field is because such boxes in different places would fall to the Earth along different trajectories. I mean, we don't see that in dropping two balls next to each other, but you can imagine what is happening is both the balls are actually falling towards the center of the Earth. And these radial lines are not parallel to each other, so they are coming closer. And that is the manifestation of gravitation. So gravitation does not change special relativity.
Sir, one request, you can stop sharing your screen so that you can be
Then
on the, yeah, so there will be a direct contact on the screen. Yeah,
Yeah, sure.
that's great. Yeah. So next question comes from Ketan Deshmukh. What big discoveries can we expect from LIGO experiments in next 50 years?
Okay, so there are, so at this point, the discoveries that I talked to you about were all of a particular kind. They were two massive objects merging with each other, but they are very different possible gravitational wave signatures. So there's gravitational wave signatures of supernova explosions. Then there are gravitational wave, possibility of creating gravitational waves from exotic objects like uh, strings, cosmic strings, and there are also possibilities of getting gravitational waves from in Lisa and all will where measure gravitational waves coming out of white dwarf binaries, so a completely different class of objects. And then there is also a stochastic background of gravitational waves, which is essentially like the residual unresolved gravitational wave, because as I emphasized to you, gravitational waves are generated in huge amount in these mergers. So this energy from various mergers must be sloshing around in the universe. So only reason we don't feel it is because to detect them would be require a sensitive detector. But what is hoped is by the time LIGO India comes up, we would already be in a position where we would have detected this stochastic background of gravitational waves, stochastic random background of unresolved gravitational waves from various sources. And that tells you the distribution of matter in the universe. And then gravitational waves, I told you, are already trying to measure the expansion rate of the universe. They can also measure what is called the dark energy in the universe. Eventually, with many events, they will get competitive and start becoming an independent measurement of the accelerated expansion of the universe.
Yeah. In between, we also have participants on YouTube live. So
Hmm.
I'll just take questions from YouTube also. There is Nimiksha Mendoka asking, do gravitational waves become weaker as they travel through space due to obstructing stars or planetary bodies?
No, gravitational waves actually are very weakly coupled to matter, which is why they are so difficult to measure. So they are not absorbed by matter like light is absorbed through matter. So gravitational waves, of course, if for a spherical source, as you go far away from it, the intensity will fall off as 1 over r square because the energy is distributed over bigger and bigger spherical surface, right? But beyond that, there is no absorption like light is absorbed through dust in distant galaxies or in our own galaxy. That kind of physics doesn't happen here, or it does happen, but it's minuscule. It doesn't really. It's not important.
There is Ujjal Mandal asking relation between gravitational waves with respect to electromagnetic.
Relation, they are very similar in character. They are transverse, so all the action is happening perpendicular to the plane in which the wave is moving. So in electromagnetism, you know that the E and B field of is actually perpendicular to the direction of motion, right? Similarly, in gravitational waves, if you look at this direction of motion, all the stretching of space, squeezing of space happens in the plane perpendicular to the motion of the gravitational waves. They're also very similar in terms of the fact that they're massless excitations, so they travel at the speed of light. And all massless excitations have two polarizations only. And gravitational waves, in the theory of Einstein, have only two polarizations. These are slightly different from how they are in electromagnetism. Electromagnetism, you rotate by 90 degrees to get from one polarization to the other, from the X polarization to the Y polarization, so to say. Here, you rotate by 45 degrees to get from one, what is called the cross polarization to plus polarization.
Same Ujjal Mandal is asking, how does LIGO-Virgo detection works?
LIGO-Virgo are, LIGO has two interferometers like the one you see behind me in the picture, like LIGO-India would be. These are, as I said, 3,000 kilometers apart. And then in Europe, near Pisa, there is another detector which is not 4 kilometers but 3 kilometers in length called Virgo. And all of them are taking data at the same time. And if there's a signal that comes from the sky, it is picked up in all the three detectors, but with slightly different time delays. And that allows you to kind of guess which direction in the sky the signal is. But what LIGO India gives you is this huge baseline of 12,000 kilometers to allow this triangulation to happen more refinedly.
Okay. There is Chintamani asking, what are typical thermo-optical or non-linear optical effects? They are likely to play roles due to high power laser, and how do we compensate for that?
Oh,
Also, there is, shall I read the
yeah,
statement?
sure.
Also, the hanging mirrors are likely to experience the momentum carried by incident photons. So, how structural aspects of hanging mirrors take care of these aspects?
This is a very interesting question. So all these thermal distortions of the uh, of the elements of the laser light do matter, and even in the laser itself, the crystals there, you have to worry about thermal distortions created by that. And that is where the technology part comes. I mean, you're working not only in fundamental science but in applied science, where you want to make sure that you have the right uh, compensations for this. The mirrors, as you rightly pointed out, not only shake due to light, but also heat up. Although the absorption is 1 part in million, but if there's a 100-watt laser shining on the surface, the mirror distorts, and that is compensated for by heating the mirror from the other side by another laser, which compensates for the change of shape. So that's what adds to the very immense complexity of this detector. So you have one chain which I showed you, which is the so-called the detection chain of apparatus, but then there is a huge amount of compensatory apparatus that corrects for the kind of thermal distortions you're talking about. And then you also asked about the shaking of the mirrors due to light. Yes, that's a fundamental um, constraint we have. So no, I mean, the steady part of the light, of course, we can put a feedback mechanism to take care of the steady part. But you know that even the most steady light source will have quantum fluctuations in the number of photons which are hitting the surface, and that jitter creates a quantum noise, and which is called the photon shot noise, which is tiny given the huge intensity, but still enough to trouble us. And that is again taken care of when we try to use quantum squeezing of light to try to compensate that for this radiation pressure fluctuations uh, against the number fluctuations of photons.
Okay. Next question is from Vaibhav Raut, says, would gravitational waves detected by LIGO India will be detected by LIGO US simultaneously? And would we be able to locate the direction of the event in the sky in such a scenario?
Yes, so the whole idea of LIGO India is to work as a part of a global network. No gravitational wave observatory in the world works alone. So even any observatory that comes up has to work together with others, because on its own, any gravity wave detector is extremely has very poor directional sensitivity. They're omnidirectional, so they can't make out, a single detector will never be able to make out which direction of the sky a signal came from. It will know that for something happened and a black hole merged, but it will not know which part of the sky. So it's only working as a network of global network of detectors that you can make progress. So LIGO-India will work in this mode with the other detectors. The advantage of LIGO-India is its size is the same as the US detectors, and its expected sensitivity is supposed to be exactly the same. So we are guaranteed to have 3 identical detectors spaced very far away from each other.
Next is Raja Nadarajan is again asking, please comment on the possibility of quantum gravity and how to handle the singularity in general theory of relativity.
These are not something that necessarily are part of gravitational waves that we detect are classical waves. So we are not really exploring the quantum domain. Okay, so the first gravitational wave was, if you convert it to number of gravitons, it had 10 to the 66 gravitons. So it's basically a classical object, not, the quantum nature is hidden. I should also mention that the fourth window that I talked about, this gravitational wave, cosmological gravitational waves, these are expected to be of quantum origin. So if we detect them, that would be the first time we detect, signals which are quantum in nature, gravitational waves that generated that are quantum in origin. But beyond that, you also ask about singularities of space-time. So, amongst the exotic signals that we could measure are signals of gravitational wave signals from naked singularities and things like that. And these are exotic possibilities. But if they happen, they would be, of course, amazing discoveries.
Ethan Deshmukh is asking how LIGO experiments relates to the neutrino research.
It again does, in the sense of neutrino also are a messenger, right? They are in astronomy, neutrino based astronomy is something that is coming up with this big large scale neutrino detectors. So you're not only studying the universe in different wavelengths of light, but also in particles such as neutrinos, then on cosmic ray. So in that sense, gravitational waves and neutrinos are two different messengers in this multi-messenger astronomy field.
Vaibhav Raut what are the possibilities of setting up such experiment in space where there is no question of seismic or vibrations from Earth's surface?
As I told you, I mean, so this is something that, of course, was clear, but you should realize that, in space, controlling of spacecraft's motion is a big challenge. And LISA, there was a Pathfinder mission which showed that they could do that to a large extent. And the LISA project will have 3 spacecrafts placed about 1,000,000 kilometers apart. So these were 3 independent spacecrafts which will exchange laser light between them and work like close to what the interferometer here was working like, very similar principles. And so it is a reality. So we do realize that, and these millihertz wavelength gravitational waves are not detectable on Earth because of seismic noise.
And Hemlata Sharma, is LIGO project similar to CERN project?
It is similar in the sense of the human nature of it. I mean, they're huge teams. So LIGO has, many engineers and scientists involved in the labs. And it's also a worldwide collaboration, like CERN has the CMS group, which is, also in India. And so various experiments have groups all over the world. So LIGO is something very similar. And it is in the line of these mega science ways, the big science, what is called big science. So these are science which require resources that a single country typically is unable to come up with, and hence you require worldwide collaboration of not only, it's not just the money, funds, it's the technology, the same technology, all the technology is not available in one country, and not all the talent required is available in one country. So in that sense, CERN and LIGO are very similar.
Advait is asking how cosmological constant can be determined using gravitational wave detection, as well how CMB polarization can be measured by gravitational waves.
CMB polarization is not measured by gravitational waves. Gravitational waves are measured by measuring the polarization pattern of CMB, the cosmic microwave background. Okay, so I thought I'll get that out of the way. And then your other question was,
how CMB polarization can be measured?
The first one.
Yeah, first one is how cosmological constant can be
Cosmological
determined.
constant manifests itself in the accelerated expansion of the universe, and gravitational waves sources also are standard candles. Just like if you know that the accelerated expansion of the universe was measured by looking at supernovae in light, very distant supernovae. Similarly, very distant sources of gravitational waves can be used to measure the acceleration in the expansion of the universe and hence determine the cosmological constant.
Our President Mumbai Regional Council, Atul Modi, is asking how do you see an event earlier in LISA compared to LIGO?
Okay, so suppose you imagine two light masses, or maybe just look at this object that is coalescing, two neutron stars that are coalescing in the LIGO band. We see the last minute or so of the whole event. But earlier, the neutron stars were still going around each other, losing gravitational wave energy. But at that time, the orbits were much bigger and the frequencies were in millihertz. And that will be first seen in LISA. So LISA will see these binaries, at millihertz frequencies. And as the object loses energy and angular momentum and starts speeding up in orbit, it sort of moves to higher frequencies. So it will be in the LISA band, then it will exit the LISA band. And then after some time, it will enter the LIGO band and will be detected there.
Kumar Hemant is asking, can these gravitational waves pass through massive bodies like Earth and Sun or absorbed?
They pass through gravitational waves. The Earth is transparent to gravitational waves. So as far as gravitational waves are concerned, these detectors are freely floating in the sky. They don't see the Earth at all. So the gravitational waves can come to you from underneath the Earth or from the top with almost equal, with the same transparency.
Devidas Gulwade is asking, does lattice phonon vibrations superposing on very small effect into bracket in comparison that is intended to be assessed causes any complication in analysis?
Phonons are not so much of a problem in this game. None of the the kind of things that you're talking about, I don't think are important in the LIGO detectors. But phonons in general, of course, in terms of looking at the vibrational modes and the absorption of, not absorption, the distortion of caused by the mirror coatings have a lot to do with science of phonons on the surface of the mirror coating.
Okay. We have Faraz maybe asking, he first thanks for such a great talk. He's asking, gravitational wave detected by both LIGO and Virgo in August 19, where a 23 solar mass BH merged with almost an object of 2.6 solar mass. What do we think? Wait a minute, I'm not able to complete that.
Sorry, who?
Wait a minute.
Can I
missed
interrupt?
that. Yeah, you can.
Can I read it?
Yes.
Yeah,
You
it
can.
says, what do you think about other object? Was it a neutron star or a black hole?
Oh, are you talking about this very recent one? We don't
Yeah,
really
August
know.
19, August
Yes.
19, where 23 solar mass black hole merged with almost an object of 2.6 solar mass.
Yeah.
Oh, okay. Yeah. So there also it wasn't totally clear whether it was a neutron star or not, because till now we have only seen electromagnetic follow-up only of one event. We have been successful in that. So if it was a neutron star, one might have expected some signature in electromagnetism, but the fact that we didn't see it does not rule it out, because we didn't know where to look. We are waiting a global array with LIGO India involved to be able to next time tell you that, okay, you know, it may not have been a neutron star because we didn't see any light from that region.
Next is Devadatta Banerjee is asking, just like electromagnetic waveguide, is gravitational waveguide possible?
Um, in principle, of course, yes, the physics would work out the same. But imagine what you'd require to guide gravitational waves. So electromagnetic waveguides are made of material that, kind of are conducting, and so you'll have to imagine gravitational waves getting funneled through some space-time structure. So maybe exotic objects that people talk about like wormholes and all could be possible waveguides for gravitational waves. But I'm offhand I cannot tell you, but those are possibilities.
Okay. This is Satyaki Goswami asking, is there any possibility that the perturbation due to gravitational waves trigger formation of stars in active galaxies?
No, not really, because the perturbation due to gravitational waves is very minor, right? Very small. So these star formation is triggered actually by shock pressure waves, shock waves that go through the medium rather than gravitational waves.
I think this question from Ujjal Mandal from YouTube saying, it is related to, I think, your PPT. Displacement units, how root exit? Please explain.
Oh, okay. So this is because you're looking at a strain in a frequency band, right? So if you look at this as a time series data, then we are looking at the Fourier transform of that, and I'm looking at the square of the magnitude of the um, Fourier modes, and then I'm asking the question how much of power is there per you know logarithmic unit of frequency, and that's where the f to the power of square root hertz comes.
Okay, it is Suman Pramanik. How the polarity property of gravity related to the speeds of different polarization of gravitational waves?
In Einstein gravity, as I said, Einstein's gravitation, there are two polarizations, both travel at the speed of light. But in more exotic theories of gravitation, there is a possibility of having other polarizations, other polarization states of gravitational waves, and they are massive and they travel at speeds related to their masses. So they travel slower than the speed of light.
Sorry, sir. The question is how the parity property of gravity related to speed of different polarization of gravitational waves.
Oh, it's parity of
Parity.
gravitation. I
How
don't
the
quite.
parity property of gravity related to the speeds of different polarizations
No, I don't
of.
quite understand that. But I mean, if you want to ask about the two polarizations, of course, they are such that they are strains, so they don't, go from one to the other under reflection.
Next is, what do you mean by stochastic gravitational wave signals?
Stochastic gravitational wave signals, stochastic means random. So if there are many events happening, just like in Diwali, for example, you hear one firecracker at a time, you can, that's like signals happening which you resolve in time. But when you have these firecrackers which are bursting one after the other, all almost on top of each other, like these huge chains that there is popcorn kind of a noise, or popcorn itself. The name comes from popcorn. So when popcorn is you don't hear the individual pops, but what you hear is a noise, which is a mixture of all the pops together. And that is the kind of stochastic noise, gravitational waves we are talking about. So there are so many binary events happening. In fact, in the universe, every 15 minutes, event like the one we detected first has happened somewhere in the universe. So the universe is awash with these signals, and these form a background of noise. I call it noise because we can't resolve them into signals, but they will be what is called stochastic background.
How do we know the origin of gravitational waves? Rajkumar is asking.
So this is related to your belief that the theory of gravity given by Einstein is correct, and in that, if there are masses moving such that the total quadrupole moment is evolving fast enough, then we'll generate gravitational waves.
Devadatta Banerjee is asking, sir, how can we say that the displacement of gravitational waves be of the unit hertz raised to half?
Oh, no. So displacement is in meters, but the measurement of noise of if there's a time series, uh, time series data, you have to give measurements. We are trying to measure the power of the noise term, and then you have to ask how much power. So if I am taking a huge wave, frequency bin, then the power will increase. So you'll have to ask per unit frequency bin, and that is where the square root hertz come from.
Okay. The next question is very similar to earlier one. Anushri Sen is asking, like electromagnetic waves, do dispersion scattering occur in case of gravitational waves?
No, not as pronounced. But gravitational waves also get lensed by clusters, just like light gets bent. So you know that light from very distant galaxies is bent by clusters which are along the masses along the line of sight that we see as gravitationally lensed objects. One does expect, as we see distant objects in gravitational waves, we will start seeing gravitational wave signals that are lensed by matter. So it does lens, but it doesn't disperse.
This next is gravitational waves have been detected. Do we have some information about graviton now? Kumar Hemant is asking.
No. These are classical gravitational waves, so these have no bearing on gravitons.
Satyaki Goswami, is there any possibility that the perturbation due to gravitational wave trigger? I think this was already asked. The question has come again. Sir, you have answered that question. And I just wanted to ask, there are about 43 questions still pinned. So do
I see.
we, yeah, do we take up all them, because otherwise it will be a too stretched
No. I think
session. I think, yeah.
I can
And there are
give you
few
my email
questions.
ID.
Yeah, that will be better. They can
People can
post it.
write to me, so I will just type out my
Yes,
email ID here
yes.
in the chat box. So this is my email ID, and if you have general questions about LIGO India,
Yes.
there is a outreach that LIGO India has. So as a spokesperson, I'm in charge of that. So LIGO India outreach at iuca.in.
Okay. So I think our participants can note down the email ID of Dr. Souradeep, and because it is very practically impossible to go through those 40-45 questions like that.
No, I think
Yeah,
that will
and
be too
it will
much.
take. I mean, some of them, of course, get diverted to some different areas. Also,
Yes.
I feel, and
So I
so
appreciate
it's
that. Yeah.
not practical. We are very sorry to disappoint all those participants to have a one-to-one talk or maybe interactive session here. But I suppose we should take a call like that. And please feel free to, I think,
Email me. Yes, please
email
email
us.
me. I would
Yes,
love to
yes.
answer, and also,
Yes, you
yeah,
can directly have a talk
yeah.
with them. So thank you
And we
very
are
much.
also there. LIGO India is there on Facebook.
Okay,
There's a Facebook page for LIGO India where you can post your questions,
okay,
and there'll be someone answering them.
that's great. Yes. So I think we have to come to an end of a very wonderful session. Unfortunately, we have to end it actually. So I now call upon my colleague from IFPT Mumbai Regional RC, Dr. Devidas Gulade, to please propose a vote of thanks. Yes, sir. Gulwade, sir.
Thank you, ma'am. It was a wonderful talk, starting with the very basics of gravitational waves, and later it covered many advanced facets related to the topic, wherein UG students really were able to relate to these concepts and enjoy it, wherein they got charged up and were asking various questions and making it very interactive. On the behalf of the participants and Mumbai Sub-Regional Council of IIPT, we thank Professor Souradeep for a very enriching talk. We extend gratitude to Director, Principal and Management of Hindi Vidya Prachar Samiti's Ram Niranjan Zunzunwala College for extending all infrastructure for the conduct of this lecture series. Also, we thank Professor Ghurpade and all faculty members of Department of Physics of RJ College for all arrangements and planning related with this lecture. Last but not the least, thank you all participants for your interest and active participation in this lecture. Over to you, Professor Ghurpade, for further announcements. Thank you.
Thank you, Dr. Gulade. It was a wonderful evening and participants were wonderful. I think having such a great feedback from the participants is really encouraging to us. As you all know, most of you know that we are conducting a series of lectures under the banner of IIPT Mumbai Sub-Regional Council and the Department of Physics, RJ College. We have the next lecture on Tuesday, 30th of June, by Dr. Anvesh Mazumdar from Homi Bhabha Center for Science Education. Anvesh is a national coordinator for Olympiad examinations, physics examination, not physics, science Olympiad examinations. He is going to talk on exoplanets on that day. Of course, we will send you the notifications, the poster regarding that, and please register again on the email ID that is given to you. So we are all meeting and looking forward to meet you all wonderful participants. Thank you each one of you. Thank you, Dr. Souradeep, again to be with us, and we wish that you will be always with us. Of course, and association with you will be a long lasting. And thanks everyone.
Thank you very much.
Yes.
Thank you very much.
I request Dr. Kiran Porvankar to please end the meeting.
Okay. Thank you, Tarun.
Thank you, Kiran. Thank you, Dr. Gopal.